But there is the ASTM is D4945, which gives all the ins and outs if you want to get into some of the details of it. But simple definition, if you will, or approach classification is real-time monitoring of the pile as it's driven. So the strain gauges and accelerometers measure various facets to the pile driving, and it gives the person on the ground, or actually they're setting up these days remote sensoring, so even guys back in the office can watch real-time data from the field. I still generally like to be on site and be able to stop things if something's gone awry or something like that, but it's basically real-time monitoring of the pile as it's going down. And one of the main things and this is going to be a huge part of our discussion, is going to be it's a method of verification, because we're taking actual measurements. We're basing it on a good amount of theory and mathematics. We can correlate that to a higher degree of certainty to our design. Anything else you want to? Is that okay? I'm going to let Dave talk about the verification method. This one's your big one.
Okay, sure. So, first of all, it's like, you can define the loads from a structure pretty carefully. We all know the way the material is going to be. We can decide what kind of live loads we're going to have. But the question is, like, how much can the pile actually hold once you install it in the ground? How much is it going to push back? How much can it hold? And so, you can't just like trust us geotechs to tell you what it's going to be, right? So thankfully we've got these verification methods, and there actually are ways, at least in AASHTO. In my world, it's mostly AASHTO, not IBC. So if this might conflict with some of the IBC stuff, but there's two different kind of camps of verifying capacity. You can have like the dynamic methods, which is what we always use, well, not always, but predominantly use, and like a static method. Static method is when you calculate empirically what the capacity should be, and you apply a reduction factor to that to accommodate the uncertainty. And there are appropriate times to use that. You can't trust the blow counts in the material. If you're in ice or something like that, and the blow counts might be inflated, you don't want to trust the blow count to give you a capacity. So you kind of look at the soil and like what should it provide, and then you kind of go according to that. But we kind of mostly live in the dynamic verification camp, which, and there are four predominant ways to verify capacity. You've got the static load test, which says static, but it actually is dynamic because you're actually moving the pile to give you a capacity back. And then also the dynamic testing, what we're talking about today, the dynamic testing, the PDA, we talk about where you're attaching strain gauges and accelerometers to the pile to measure exactly what it's doing when you hit it. And you know how hard you're hitting it, you know how it's moving, so you can kind of back calculate what kind of capacity it is. And then the wave equation, which is essentially the same thing as the PDA, but you're not measuring anything directly. You're just using kind of just what's
literature value.
Yeah, just values, presumptive values out of the literature for types of soils and the types of piles you're using. So it's not so exact, but it gets you pretty close. And then you have the pile driving formulas, which have been around ever since piles have been around. You just kind of figure out what kind of load how much energy, what's the weight of the hammer, how far you're dropping it, and how many blows per foot, and just kind of back calculate what the capacity should be based on your observations. So, and I guess the one thing to note here is when you're talking about capacity, a lot of times, when I talk to structural engineers, there's this idea that like the capacity is like one actual number, and we kind of make it that way. We talk about it that way, but we could probably talk for an hour about what the capacity of a pile really is, because like any material, it has its own modulus. Like the soil pile system has its own modulus, and it's only pushing back depending on what kind of soils materials are there. I was talking to a very respected structural engineer about 10 years ago about this, and the topic came up like what's an acceptable amount of settlement for a pile, and his response was 0. Like he thinks it should not move at all. And, I guess that's kind of where we like to be when you factor up your loads beyond what you're, actually going to use, and you kind of factor down your resistance. You kind of live in this camp where, you've designed it way over what it should really see, and you really shouldn't see a lot of movement. But the reality is, when you load a pile, no matter what, it's going to move down, either strain with the steel, or the soil will strain. So we could talk about, like, what is the definition of a capacity? Because you get this kind of modulus curve as it settles as you load it. And so when we talk about what's the capacity of the pile, it's kind of this almost arbitrary number you just assign to a curve. And there's several different ways to do that, Davison method, and there's other things that kind of define what a capacity is. But it's important to know that capacity is kind of a concept more than like an actual number. So yeah, we live in the kind of the wave equation dynamic testing zone, because that's where you kind of get the most confidence with the least cost. So, is that it?
I know the next one's photos. You want to show those?
Oh, you can talk about that.
Oh, yeah. Yeah, no, thanks, Dave. Appreciate all that. It's good context and good points. So what's this kind of look like? Back to our parts and pieces roadmap here. Just a couple of photos of what it would look like kind of up close. If you're attaching sensors here on the left side, as I go, this is kind of moving away from the pile, if you will. So once a pile kind of gets lofted up in the air and you're driving it, a lot of times you have the sensors attached to the pile. I will quote them. My yellow cable there, actually, there's another, I hang the pile or the cables from the pile towards the top. So that's just not, it's just kind of an extra thing I like to do for cable management. But you can see the sensors. If I can get my mouse over here, you can see the sensors kind of over here. And then on the right, there's just kind of backing again away from the pile. As you can kind of see them sitting there on the side of the pile as you advance down, and you can kind of still see the cable. So those are the sensors that you'll usually see, and usually there's a pair of them on either side of the pile. Occasionally, there's reasons to actually do all four kind of quadrants of your pile. There's reasons we would do that, but most commonly you'll see just these sensors on diametrically opposite sides of the pile. So the left side here, the longer piece is your strain gauge, and then your smaller rectangular one is your accelerometer. So just to also kind of know, and we drill and tap these sensors to the pile, so then that way we can bolt them on. Drilling and tapping is a very painful process some days. So if you can get the contractor to do it, that's really cool. But moving way further, you'll see a lot of times some kind of computer which collects the data. So here on the left is just sort of my cable running to my box. I stick my computer in kind of this little box just to help protect it. For those that haven't seen an impact hammer, a lot of times you get a lot of spray and diesel oil kind of coming off of it. So just to kind of keep yourself a little bit cleaner, I have this box. It also is nice if it starts raining or something like that, I can kind of close it. And then just on the right is myself, just monitoring it as the pile's being driven. I can see the data real time, and so if I start to see something progress or see something very strange, I can stop them. And we'll talk a little bit as we go what kind of things we see in that data and how things kind of trend during data collection in terms of that real time, why I like to kind of be there on site. Just a real brief history. A lot of the wave equation stuff and the background of PDA starts in about the 1950s and the 1960s. In the early 60s, there was a paper by E.A.L. Smith, who wrote kind of the first early version of a program for the computer to discretize the pile and run through the finite difference equation, set of equations for the wave equation. It's a fourth order differential equation that we're solving for. And so discretizing with finite difference allows you to solve that with all the different inputs. Around that same time in the 60s or so, there was research being done at the Case Western Reserve University, which led to the Case method. They were trying to interpret the wave that they were collecting, and they were kind of generating this kind of pulse during a drive, and they were trying to correlate that to pile capacity, which led to this early Case method. And even today, you might see If you get your outputs from a PDA, you'll see the case method usually mentioned. It's not common these days because we have CapWAP, which we'll talk about later. But it's the early method that's still kind of around. And there's actually a few other different approaches. There's an energy approach, which you'll see, which the PDA all spits out all these numbers if you want to get really crazy about it. Those methods are really nice if you have yourself kind of calibrated and you know your site really well. You can use them, but they're just not commonly used. We later transitioned from this finite difference approach to a method of characteristics to solve the wave equation. It's another way to use math to solve that differential. And then currently we have the ASTM 4945 that provides guidance on performing the PDA. And then there's a whole host of papers online you can go read about. I put a link at the end here, but the guys that make this equipment is Pile Dynamics Inc. out of Cleveland, Ohio. They host all their papers online. You can find tons of the stuff about PDA as well as a few other subjects like the drilled shafts. So very, very basic principles of the wave equation here is that we're treating the pile as a rod acting like an elastic spring. So we have this pulse coming down from the ram. It travels down the pile. In this case, it shows a soft layer hitting something hard and starting to reflect back here on the far right. And what we're doing with the instrumentation is we're measuring that wave. And so you see on the left, the curve that's kind of produced, or the wave that we record. And you'll notice there's kind of two there. There's a force and then there's a velocity. And we use those two separate, but yet together. The strain gauge is measuring the force based on the cross-sectional area of the pile and elastic modulus and those properties. And then the velocity is being recorded with the accelerometer after integration. It takes one degree of, or one iteration of integration. And the reason we do that is sort of it's a self-checking kind of system. We essentially have two different methods that we're using then together. They're related to the pile through the impedance, and we're able to help validate our data essentially with that impedance. And so you can see on the right where the two waves kind of start on the left side and kind of ramp up with that moment of impact. One of the things you're looking for is as close to matching as those two can be is one way to kind of check your quality of data. So if you're seeing, and we'll show some stuff later, if you're seeing curves that are very off from each other, there's ways to interpret what's going on based on those curves. But this is what we're looking at. So when I'm standing at the computer, that wave basically on the right is one of the ones that we're watching for, as well as a host of other kind of numbers. This is just another illustration for how they used to model that hammer pile, but some of the soil properties are kind of illustrated here. We take the pile and we're looking at different segments. We're looking at a damping and a quake for each of those segments, modeled by a spring and a dash pot, as well as the tip. And we're going through an iterative process to then get those properties as a function of length and a function of response to that pile. The wave, we basically take that wave that I just showed you. It's essentially occurs over the length of the pile, and then we can then correlate or relate that wave to those individual sections of the pile. Is how we kind of work that, and then we're able to derive soil parameters when we do the signal matching down the road, which we'll talk about. We can then match everything up and get a good quality match to a computed wave versus a measured wave. Right now, we're just talking about kind of like the measure, but this kind of shows you a bit of the holistic, to a certain extent, or one step in the process. So we're gonna move on. That was kind of the rough way. Like I said, not trying to get too nerdy about it. But you want to tackle the pros and cons here? I know you had some input on the.
Well, yeah, I guess the pros and cons. It's kind of I know Steve and I had discussions back and forth about this. You know, let's see, what did we end up saying here? You know, I guess, you know, the PDA, when it's used, it's usually because it's being used because it's the most effective tool you have to solve whatever problem you're trying to solve at the time. And so, you know, it's kind of difficult to talk about like the cons of it. I mean, there certainly are things you need to worry about. You know, like you need to get a professional on site who knows how to do it. And you might need to wait for them to be available. You're going to have to accommodate them by getting power or maybe a lift to the site so they can drill and tap to install the instruments. Um, like I said, I say power, certainly shutting down the productivity to accommodate the testing. But generally, and so you think about that as like it's not just a free thing that happens, but the alternatives is not knowing the capacity to a very high confidence level, or spending way more on a static load test, which you don't know is you install the pile as normal. Then to test it, you have to load it, and to load it, you have to build a reaction frame. So you're driving all these additional piles to kind of withhold the uplift resistance, and then you're like, jacking it hydraulic press to kind of see how much that pile will, settle with load to get that curve and that relationship of capacity. Certainly, that is a much more expensive way to verify capacity. Also, too, there's the pros are uh, you can see how well the hammer is performing. You've got this theoretical energy that's impacting on the pile, which is like the stroke height of the hammer and the hammer weight. And you should calculate, okay, it fell this high, it weighs this much, you have this much energy, but you have sometimes like pre-ignition or like a really worn out hammer is going to have more friction in it. So it's not going to be delivering all that energy to the pile. And sometimes you'll get the diesel squirted in there. It'll ignite before it actually impacts, and it'll kind of slow the hammer down. And you'll still get a good high stroke, but you will get less energy hitting the pile because it's more muffled in there. So you won't really be able to tell it just by listening to getting the stroke and listening to it. But if the pile's not moving, you think, okay, we're getting great capacity because the pile's not moving, we're getting high blow count, we're getting high strokes. And it could be that the hammer is performing really poorly, and the PDA will be able to detect that, so that your energy being delivered is not what you think it is. So it'll kind of signal a problem that you have to address somehow. So in the pile damage, I'm not exactly sure how they do this. I think it's you should be able to measure the time it takes for the stress wave to come down the pile and bounce back up. And if you think you got a 40-foot stick of pile in there, but it's coming back way quicker, pile is shorter. So the pile is like scrunched down, and you're saying we're getting signal back like it's only a 30-foot pile. Well, you think you're advancing this pile, but it's not really fully, it's not as deep as you need it, or it's compromised at the tip there. I'm just reading what we ended up here. Yeah, and the stress is like, that is, you've got these two strain gauges on either side. So each one is measuring the stress. And ideally you'd have the hammer hitting squarely, and it's hitting, the stress is being distributed all the way down, uniformly down the pile. If you've got a big rock on one corner, that it could be concentrating stress on there. And when it bounces back on that corner, it'll show you're getting higher stresses in that one corner. Or if the hammer's kind of hitting cockeyed, you're going to be getting it coming down, eccentrically on one side. So you can tell if you're just getting higher stresses than you can handle. So a lot of times we say you need like 90% of the yield stress of the steel to limit the stresses so you don't overstress the pile. But usually when you calculate that, you're assuming an average stress distribution over the entire pile section. And if you're getting some big boulder or you're getting an eccentrically loaded pile from the hammer, you can easily way exceed that, and the PDA will tell you that. And I was thinking like the cons. I guess one thing we talked about was like the cons. I don't really see cons because anytime you're using it, it's because it's the cheapest, quickest tool you have in the box to solve your problem. So I don't really see cons to the PDA, but I mean, certainly it can be overused. Sometimes if you're in I've seen projects where you've got, it's like a pedestrian bridge, like a two pile abutment, big H piles down to, really dense material, only being loaded to, very small loads. And so to mobilize, a contractor out to do the PDA might be overkill because the piles can handle lots of stress. You're not going to hit them that hard. You got good bearings, so you don't really need to worry about capacity. But so it's useful. It's in our standard spec. It's what we presume is going to happen on every project. But there are certain times when it's not really needed. So.
Cool. No, appreciate that. Yeah, we went back and forth on the additional cost comment. We're still a little at odds with that, I think. So what's that? It's a great question. Actually, we're going to talk about that right here. One step ahead of us there. So one of the biggest disadvantages is a lower factor of safety. And I really liked what Dave provided from the AASHTO perspective. Gives a bit more comprehension. The IBC doesn't give as much. It kind of talks about it relative to your design stresses. That's that reference in 1810. But it doesn't give you a whole lot more guidance to it. So AASHTO gives you a little bit better. It kind of says, well, how can I lower my factor of safety based on what I'm willing to do? Because this is a construction verification technique, and allows you to then alter from there. So like AASHTO will actually let you go and do static load tests, 1 or 2 per site, and you can see the factors of safety that get generated. Dynamic testing, if you did 100%, you get quite a bit lower, but yet or in the realm of a static load test, if you do 100%, maybe those costs are fairly equivalent. I'm not sure, but could be. Usually what we see is kind of that fourth one is a dynamic testing, and usually like DOT is usually at least 1 pile per abutment?
Per bent, yeah.
Yeah, per bent, okay. Usually it's about 2% is the recommended based on your site conditions. So if your geotech says you've got pretty variable stuff, you maybe need 5, 6. So 200, maybe something on the order of anywhere from, as little as probably 4 to 10 maybe, depending on your site conditions. And that's something you can consult with your geotech. Usually I mentioned in my reports doing this when I do deep foundations. I usually talk about the wave equation versus PDA. Most of the time when I've thrown out static load tests, nobody wants to do that, which is understandable. But occasionally it's required and beneficial. But usually it's a small percentage, like I said, and then you can use a little bit lower factor of safety. Most of the times we see, I think, in what I've seen around Alaska, maybe with DOT exception and a few other entities, is the wave equation. It's usually a desktop study that's done ahead of time. Some presumptive values are used, and then you go out and you count your blows and you call it good or not. And I think many times it's valid, but there is some variability, as Dave was pointing out, about the energy transfer, about the soil properties. So your factor safety goes up a little bit more. So where the PDA comes really handy is if you're kind of on the cusp and you find that having to go a little bit deeper drives up the cost quite a bit, and that's where a big zone of PDA lives. Is you can shorten up those piles a little bit, and it usually has downstream effects. We did a large static pile load test in Yellowstone years ago, and I did PDA in the piles, and couldn't figure out why we were spending $1 million on a pile load test. And the FHWA engineer, because we thought it was just materials, and FHWA goes, no, we're working in Yellowstone. So this 7-span bridge, if we knock off an entire segment of pile length over all of those, we reduce construction down to 1 season. And he went through all these benefits, not just materials. So it was very eye-opening. So there's definitely all these parts and pieces that get added in, but and then there's Gates dynamic formula. That's an AASHTO pile driving formula that's used as well. And then really old pile driving, if you want to do ENR formula. I don't think most engineers today know even what that formula is, but I should show it to you. I have this old thing from DOT. My dad had it. Was the old ENR formula. It was like a slide rule kind of thing. It was really cool. I should have brought that. I'll have to go find it. So another one is, like we mentioned, is the stresses during pile driving. As we drive the pile, we generate stresses not just concentrically but eccentrically. So we want to know kind of both. Usually for steel, we allow 0.9 FY. It's really common. And then there's some other ones for concrete and timber. Don't really deal with those, but if you do, there's some guidance on how to address it. There's also some discussion about tension limits and things for other types of piles, but most of the time we care more about our steel piles. So, but if you are driving concrete or something, you have to be more mindful of the tensile conditions. So what does that look like in the field? So these are screenshots that kind of come off the PDA output. We won't go into all of these here. I repeat them again later. But from the stress test standpoint, the top three are kind of usually what we're monitoring in the field. The top one is the CSI. It's the individual sensor. Is what's an individual sensor picking up while it's driving in terms of the stresses. The X is the average of the 2 or 4, however many strain gauges you have, and then the B one, the CSB, is the bottom stress that you're seeing there at the toe of your pile when you're driving. The CSB can be a little bit deceiving if you've got like a shoe or something on the bottom and you've got a much thicker wall kind of down there. So a lot of times it's conservative anyway, but you do want to be mindful of your bottom stress. As Dave mentioned, if you hit something, you can start to overstress it. On the left, I just wanted to show kind of like this is probably a bit more of what we would like to see. Maybe a fairly even balance between the individual and the average, and bottom stress kind of is what it is. On the right is one where we're seeing a significant spike in one of the sensors. And that's the kind of thing we want to start watching for. It may be just a particular moment in time, and maybe the next blow is going to be good, but that stress number can start to propagate and increase. And there's some other things you see, not just that number. There's some waves you can kind of see that indicate what's going on. On that note is we get into that eccentricity. So we start to see one sensor start to see more load. Usually that's something we want to avoid and minimize the risk of damage. As you saw, that was 38 KSI. I was on a job this past summer that they started to see some 50 KSI stresses on an individual sensor. And it wasn't, as far as I could tell, they weren't hitting anything at the bottom. It was the crane operator not paying attention and not lowering the hammer properly. And so the hammer was starting to lean. And as soon as I told them to straighten up, the sensors were showing pretty concentric striking. So that's why we put them on the opposite sides. Like I said, if you're really concerned, usually spirally welded pipe is one where you'll see 4 strain gauges across the pile. But if you also know the hammer is suspect, you can do that. And like I said, it increases the likelihood of damage, and realign it if that's what you see is kind of going on. But that takes a bit of experience working with your crew, and maybe the first pile you don't necessarily know it, but usually by the second or third pile you can kind of tell that your crane operator is maybe not paying attention. And I know he wasn't, because he was on his phone most of the time, so I know he was not paying attention. I won't call out the company, but they were nice guys. So what you see though, aside from that number, if you're watching, because everything comes up on the screen, and you only have is one of the challenges of it, is you only have a second or so before the next strike of the hammer and your next thing comes up. So if you're seeing something, you need to stop and say, hey, I need to review the last few blows because something's going on. But another way to do it, and this is how I like to do it in the field, is I like to turn on the display, which I think I have later in the presentation. You can set up a couple of different curves on the computer screen, and one of which is that I alternate is this one, and this shows my pair of strain gauges. And the big thing here is you can see they're not very well aligned, right? They're offset quite a bit, and that's where you're seeing that eccentricity. They should be more or less on top of each other or pretty close to it, but they will. But if they're not, then that's where you got to kind of see what's going on and try to chase down that or run the risk of damage to your pile. And one of the piles we had, there was damage to it, and that was fortunately not a DOT project, but they had to extract the pile and rederive it. But the other One that's really interesting that Dave mentioned was the energy transfer. I actually wrote a paper about this a few years ago because it's a fundamental input to not only the wave equation, but it's a huge part of what we do. And it's not always noted that there is a loss of energy. And really what you don't know is what that value is, but that's where the PDA has that advantage. In theory, it's this ram weight that we're driving. It's falling a weight, falling a distance, and so from physics we know, but through a variety of things, we lose a lot of energy. And when we look at the actual numbers that get transferred to the pile, it's usually somewhere in the range of 40 to 70% of the hammer energy. Something around 60 is really common, but you can see quite a bit. I worked on a job that the contractor had used the pile or the hammer and drove the piles really, really hard because they opted not to pre-drill. And on one abutment, and when they moved over, I noticed that the hammer was really, really inefficient. And so, yeah, you're getting 150 blows a foot. I think you got all this capacity, but realistically, when I did all the PDA work, the capacities were pretty similar, even though they thought that one abutment was going to be a much higher. And it came down to the energy transfer. So it's a critical input that we don't always know. And one of the big reasons, aside from soil properties, that pile driving formulas are pretty limited and have such high factors of safety, because you don't actually know. If you have a rough idea what your hammer is, or know kind of the range that you would expect, the pile driving formulas can get a little closer at times, but you have to kind of know ahead of time. So this is just kind of an example that came from that same project that I don't actually remember which project it was, but where the screen here on the far right is that same one that we had from earlier, and we have this energy of 36.2 kip feet. That's the energy that the pile is actually feeling from that hammer. The PDA measures a stroke, which is the STK of 8 foot, and so if you use that, you get a much lower transfer of 57% than, or not much lower, I guess it comes out to be 57% of the theoretical from that point. That 40% is a little misleading, the ETR. That's actually the maximum that from the hammer. That's the percentage if you were to use the maximum energy of that hammer. We seldom ever see that, so I don't know why they include it, but that's the default in the PDA program that we use. But usually the ASTM requires you to spit out that energy transfer percentage. And some of the other numbers here are having to do with the other methods, like the RXs are that case method with different soil parameters assumed. The others are some energy methods and some and other just basically simplified methods based on the pulse. So if you've got a really dialed in setting, you can use some of these other values to get capacity, but we won't get too much into that. Another one, like Dave mentioned, was the damage. Dave is correct in terms of the velocity. That's essentially how we do it. Where we look at where the velocity changes, and we have to know where damage occurs. This I stole from PDI directly. We represent it in terms of the beta, and it's usually a factor relative to that velocity, but a change in cross-sectional area will change the velocity, and they represent the wave down versus up, which is what you're contrasting to get that assessment of damage to a kind of a percentage of what remains. There's some guidance generally on what's acceptable. Some amount of it is of damage might be okay, but and sometimes you can get false positives off this as well. So you want to make sure that you thoroughly kind of inspect, because a lot of times like your welds can actually, because of the change in cross section some of the time, and so it can signal, and so when you're driving, you'll see the screen, and a lot of times you'll see something indicate damage, and then the next blow it drops off, and that's not usually an indication that you actually have damage. You're watching for what you see kind of on the right here, where you're seeing this red line. You're kind of watching for that location to repeat itself multiple times, and that's usually the moment you want to stop everything and start to reassess what you got going on. And then the big one is pile capacity. That's usually like 80% of why we do this, is that verification for our driven capacity. I've done other projects with these other stuff, and I tried to find the photos of that Moose Run bridge. I couldn't find any of Ellen's photos of me doing this out there, but on that one, I did look. I found a bunch of photos, but I didn't find any of me doing it. But on that one, we had to just look at the stresses. So sometimes we don't care, but capacity is a big one, because it's more reliable than and doesn't have the assumptions than others. And we can, like I said, we can match that wave. We can actually measure the wave. We can go back to the office and we can go through the math, change a bunch of variables to dial in what our compile's experiencing at that moment in time, which is a huge benefit. It takes a little bit of time. Maybe that's a con. It can take a little bit of time to process that data. Usually a couple of hours or so, but it's definitely faster than a pile load test, and certainly more certain than a wave equation. Oops. Okay. And in that vein, I wanted to share this one that I did with a previous company, where we were driving some skin friction or some frictional piles in some soft marine silts. And one of the things you can do as part of your design is include a restrike. So you drive the pile initially, you let it sit for a period, and then you come back some time later, strike again, and you can measure how much additional capacity ideally will get generated. Some soils, certain ones will relax, but most soils tend to add capacity with time. So this is one where we restruck the pile after 3 weeks and 6 weeks because of just how low the initial end of drive skin friction, which is kind of on the far left of that plot, was only about 144 pounds per square foot. We needed quite a bit more, so we went in and we did these restrikes to see how the setup would be, and that way we could apply it to a lot of the other piles, and it was pretty beneficial part of the design. It actually helped us quite a bit. We thought that there would. I wasn't part of the design. I was only doing the testing, but the design team thought that the capacity would just simply be higher, and it wasn't. So we went through this restrike, and we go in there and like I said, we strike the pile, we mobilize it just enough to get some measurements, and then we can redo all the analysis and then see how things have increased. And these are just averages over the length of the pile. So you can plot these up, but this was a fun exercise. And this silt, I mean, we got over double the capacity in 6 weeks. So it's definitely an option, something to think about in your designs and things. Couple of the disadvantages to the PDA is the pile movement. The PDA itself is relying on a certain amount of movement to the pile to kind of look at that wave and look at the soil. But when you kind of hit the extremes of soil, so you find really, really soft, loose soils or really, really hard soils, the PDA tends to struggle a little bit more. You can still collect the data, but your values and your computed capacities can vary a little bit. When you're in really, really soft material, the pile basically can just move too fast or too far. And so your calculated capacity there could actually be higher than your actual capacity. Whereas in the opposite occurs, if your movement is too small, your calculated capacities are probably way under what you actually have. So there's some guidance. I don't know, you have any guidance on the blow counts, that the range, what was it, 30 to 80? Is that what you guys want?
30 to 120 is
30 to 120. Okay.
Is the normal operating of a hammer.
Okay. Yeah. So yeah, when you're into the teens and 20s on your blow counts, can be a little bit difficult in the field. And then definitely when you hit 100, it's kind of starting to there's just no movement in the pile.
The contractor doesn't like it when their hammers are operating above 120 blows a foot because they're just working really hard. And that's what we define that as difficult driving conditions. And so if a contractor's doing 120 blows a foot and we've assessed the hammer's working fine, it's not a hammer problem, then they're usually entitled to more compensation or some other, alternative ways to advance the pile. Either, it's like, it was a surprise to us and to them. So, pilots, special pile excavation, like cleaning out, the tips if you can, or getting a bigger hammer or whatever you can do to advance it. It's generally not on them if it's into difficult driving. And also too, if you've got too low blow counts, it becomes really difficult to assess capacity because um, there's so much. If you're, the difference between 119 and 118 blows a foot is not that much. It's you're kind of at that flat part of the curve. But between like 10 and 11 blows a foot is huge difference in percent wise of capacity. So we'd like to have it. I think it's above 15 or 30 is where we'd like to see kind of the county blows. And if it's again too high, too few blows, a lot of times they can throttle down, like just reduce the amount of fuel that goes into the hammer, and so you're getting the lower stroke, so you're not hitting it as hard, so you can control blow count that way. But
yeah, that's good. That's a good point about the hammer. There are some things the contractor can do. A lot of times you'll help size the hammer at the beginning, so the hammer is sort of in a good range, and the PDA is then kind of helped out in that respect. And then another one is that it's not an actual pile load test, but it's simulated. It uses those quake values, these like small displacements, the way that remember back when we discretized it, you have these really, really small displacements along the pile length. You kind of add those up and they kind of mimic a pile load test. Is kind of the idea, but it's not an actual one. There's some good correlation between pile load tests and the PDA, but obviously it's not. So that's why the factor of safety is slightly higher, but definitely lower than just a wave equation. Usually you're within 10 to 20% of a pile load test, but there's still some variability there. Let's see. The considerations that we had has long changed. Yeah. Again, not a large cost, but there can be a little bit of cost to get somebody out there. Obviously, it can vary a little bit, but there's things to think about when it comes to some of the costs. We wanted to kind of mention about the location. I did one this summer that was a full day of mobilization to get to the site, so it definitely can take a time if the contractor's waiting on me. Obviously, the number of piles tested impacts it as well, and then the efficiency of or loss of efficiency on the contractor side. Usually they'll build it in, hopefully to their bid, that they got to help the PDA person. But yeah, usually like Dave was saying, you got to get a man lift out there, you got to go up, you got to attach sensors, start driving pile, and then if there's a problem, sensor comes loose or something else, you got to go back up, and there's a little bit of loss there. So it's just things to kind of keep in mind. One of the things I added as a consideration too is the capacity determination in permafrost is not valid. It's not a method for permafrost axial capacity. Everything else still works. Energy transfer stresses still valid, but actual capacity, because of the way piles in permafrost are designed and behave and interact with the frozen soil, assuming it's bonded, is different. So that's just something that we wanted to point out. So what do you get out of it? Sorry. I have a hard time filling the hour. All right, that's great. So you should get a PDA report. It'll include a lot of this information. Kind of documents everything is really what it comes down to, including the pile capacity, that energy transfer. These are all items that come like straight out of the ASTM. Is the reported values. One of the big ones is if you want the soil properties, it's super useful because then you can do a refined wave equation. You can essentially you can take the outputs from the PDA and go into another program, Gero Wheat, for example, for the wave equation, plug in the same values, and if you got the hammer performance kind of dialed in, you'll get the exact same answer. And so it's a much higher degree of reliability if you have what's called the refined wave equation with the actual soil parameters at your site. Just some screenshots from the reporting. The left shows, I've been mentioning this computed versus measured wave, and that's what's here on the left. The black is what was measured. The blue is what's computed. Like I said, you kind of iterate a lot of about probably 15 to 18 different variables to get these waves to match. But that's kind of the goal. When it's matched and you've got a decent output, the simulated load displacement curve and values there on the right are what you also see, and you can see where it breaks down the total resistance, the skin friction, and the end bearing, and then at what displacements you would need the dy and the dx there. Usually those are about the same, but because they're pipe piles, so there's no differences there. And then with the set is just the set. That's basically the blow count, but inverted. You also get a distribution of skin friction along the pile and some summaries. This is how you can kind of know that everything was kind of up to snuff. You can look at the embedments and the cross-sectional area. The cool thing about the PDA, one thing I did a job a couple of years ago where I had a different pile size in the computer from the last job, and I forgot to change it. And I collected all this data. I thought there was all kinds of problems, and then realized when I was looking at my output, my cross-sectional area was wrong. And so I changed it in the computer, which you can do because it's all recorded data. And then the answer flushed out much better. So it's somewhat self-saving in that respect. And the data is recorded real time. I did have one project with the failed on me during, but it actually saves the data in the computer, and so you can go find it even if it fails mid data collection, or if there's some problem, you can actually go and find it and buried in the computer. That was nice too. But this gives you a distribution and kind of knows if you're looking for specific capacities, or sometimes this is useful if you're trying to optimize a pile design. That's kind of what we did with the pile load tests in Yellowstone. We were looking at those unit skin frictions, trying to find the right zones and see how long we can change, or how we could change pile diameters and things to optimize the design. Kind of a unique example. Nobody from P&D is here. This is actually a project we did where we instrumented with the PDA a modified spin fin design with some upper fins, and we got some interesting data. Didn't publish it, but it was just kind of fun to kind of see. I'm not sure how valid the capacity is with the PDA on this particular thing, but it was interesting to see the signal responses on the curve where you've got some upper and lower fins. You've got a little bit of end bearing for the upper and a lot for the lower. So it's kind of a unique design. We designed that one because we had some pretty crappy soils, and the owner didn't want a pile longer than like 30 feet. So we had to figure out how to get a lot of tensile capacity. And so we went with this design. But I happened to be the one in the field, so I told the contractor I wanted to do something real quick, and he entertained me to let me do PDA. So I always thought this was kind of an interesting idea. If anybody wants to talk about fin piles, I'd be happy to chat more about it. Let's see, on the design considerations. So how do we incorporate? Like I said, there's a mention in the IBC. There's a fair amount of discussion in AASHTO, but usually it starts in the design stage. We're thinking about our foundations, and one thing that Dave was good to point out was working with the geotech pretty close as well, to kind of figure out what would help. Maybe look at some numbers in terms of cost and say, well, would something like PDA help save cost, or where the IBC calls for the requirement to actually do it, because there is that section in 1810 that does say you have to do it under certain conditions. You can also do a pile load test, but like I said, we don't generally do that. Let's see. Things also to consider, aside from just some initial planning, is to think about the wave equation and going through and doing a refined wave equation. If you've got a lot of piles, a refined wave equation comes in quite handy. You can do a little bit of PDA, and then you have inputs for your refined wave equation, and so you have a higher degree of certainty still using the wave equation, which is, again, that's way cheaper than even the PDA. So yeah, like Dave said, work with your geotechnical engineer to determine the depth at which reasonably expect to achieve the driven capacity. And then if you want to do, and then think about, are you doing continuous monitoring? Do you want to do the last little bit? Usually you want the last 20 feet or so is a decent amount. When I was taught how to pile drive by Keith, he emphasized, he said that, Keith Corey was the former foundation engineer. Keith emphasized that, he didn't care about the upper 40 feet or whatever it was. But as we got to our bearing layers and things, we became more interested. So you think about that in terms of planning the PDA and the design, in terms of, how much data do you want? And then any restrikes if you think you're going to want it. A lot of times the silts are ones where it's good to do a restrike a couple of days later, give them a little bit of time to kind of set up. Sands and gravels, especially gravels, not as beneficial. Clays, good to do restrikes, but it can take a really, really long time, and that's usually not as realistic. So usually the silty sands, the sandy silts get the most setup and in the least amount of wait time for the most part relative to their setup. So again, on the specs, ASTM 4945, make sure folks are following that. How many piles do you want? Do you want specific ones tested? Sometimes folks want, I know FHWA does that. They want a very specific pile tested, and that's fine. Then again, how much data do you want, and any restrikes, and the questions for the restrikes to kind of ask her, how much wait time do you want? Usually it's 1 to 3 days. It's pretty common, but sometimes a week or more, depending on what you got going on. Give yourself a warmed up hammer. So hit a pile that's not your test pile. And then how much penetration? Usually on the order of 3 inches is usually about as much as you want for a restrike. And that only is important because sometimes you start to get right at the edge relative. The contractors try to be as minimal as possible, so they don't give a lot of extra room to drive that pile, and you're kind of down. I did one job where we actually, in the Yellowstone, in one of them we had to send the sensors. Fortunately, we had a oversized corrugated pipe, but we sent the sensors about a foot down below grade because of the restrike distance we had to go. So, anything else you want to add, Dave?
Yeah, just say,
the last half.
just some closing thoughts was, I'd say be wary of your geotech if they're super confident of their pile capacity chart. Because there's as many methods to predict that as there are geotechs, I'd say. And so we had a consultant give us a report one time who used probably 10 different formulas and presented all 10 different chart graphs and say, well, pick the one you are most comfortable with, and I'm like, well, that's your job. And that's the hardest part of my job, is to come up with that chart, all the liquefaction, all the stuff is, spreadsheets, and you can do it. But you're kind of putting your name on the line when you predict a driving capacity with depth chart is. And you can look at the soils, and I get surprised all the time about how things either way harder to drive or piles run. So it's definitely a difficult part of the job. So I mean, and then that's why we have these verification methods in the field, because you can't really trust these static formulas, empirical formulas to predict capacity. And how do you work with Steve? How do you go back? There's that slide with the arrows. I wonder how many far back it is. There's one that had all the factors of safety on there, and I wanted to, getting close. Here we go. So, there is a time and place for each of these methods to use. In fact, I was pushing for a static load test out at the Sewer 75-90 project, where we had 5 bridges out in that portage area, and the material was all the same. It was all super deep, super soft silts. And if we could drive, do one static load test to get a sense for how those piles are going to go, we could order, the right quantity of piling. We could drive them to a certain depth without having to stop and measure gas and weight. So it would have been really beneficial. So those are great for when you've got a lot of piling to drive in very consistent material. Typically our scale projects are, single span bridge, or maybe, double span bridge. So not very many piling. You wouldn't really pay for a static load test, considering how easy it is to do dynamic. But we typically go for, that 0.65. What we count on having dynamic testing on the site, just because all the benefits it provides in addition to capacity. We'd only use wave equation only with no testing if we're just really sure we're going to be fine with driving stresses and getting capacity, like on a bedrock or super dense till or something. But generally we're in that 0.65, and it has some benefits because, like I said, you're not exactly sure where that pile is going to stop. You have your minimum penetration you need for lateral capacity. Then as soon as they get that, then they need to get that axial capacity. And if you get to that estimated tip and you're not at that axial capacity, like what do you do? So you can either just keep on driving and hope you hit something harder, or you can start going up that ladder, and you can, the first thing we do is like do a restrike. Okay, like let it sit overnight or over lunch or, end of shift or something, and come back and let those soils kind of dissipate their pore pressures. And, the thought is that the silts will kind of lose the high pore pressures, and it'll kind of glom back onto the pile. And then you can do a test. And PDA is great because if you don't have PDA, you're trying to measure blows per foot. And as soon as you hit that pile and you start moving it again, you're going to go back into that residual strength. So it might glom on for a foot or two, but as soon as you start moving it, it's going to lose that. It's going to activate the pore pressures again, and you're going to get back into that residual strength. And so the benefit of the PDA is that you can hit it once or twice, and it'll get at the strongest point of the pile, at that low in the pile, and you'll get that measurement. And so you'll be able to detect in one blow what the capacity is versus having to, how many blows per foot was that, how much did it move in that one blow, like quarter of an inch, or so it gets really hard to do it just without the PDA. And then if that doesn't give you that, then we can say, okay, now we can scale up and go to 100% production piles, just do more testing. So now all of a sudden you don't have to drive it as hard because now your factor safety just went down. So now you might have been looking for 1,000 kips. Now if you're doing 100% production, maybe you only need to do 800 kips. So it's like, okay, if we test it, all we got to do is 800 kips. So you can reduce the demand on the pile by doing more testing. So, you always want to leave a little bit of like, insurance policy, and certainly we've gone where it's like we're just going to plan on a restrike, or we're going to plan on 100% production because we know we're going to get it. Because like we planned on restrikes at that 75 to 90 project because we knew that we're going to get a lot of setup on those piles. So we put it in spec to say 24-hour restrikes. So I like this. So, any questions?
This is kind of back in the future for me. Dr. Goebel, who started that firm, PDI, my name's Ed Case. He went to Colorado. That's where I went, got my master's. And he hired me as a research assistant because they had noticed that if the pile driver was off, they can tell from their readings, but they had no analytic verification of it. So he had me write a dynamic finite analysis program to test that, which I did, and did a 2D version of a pile. I think he would have liked me to have gone on and done a 3D version, but I didn't have enough time for that. And yeah, it verified that, and when that wave goes back, it's definitely off. You can realign it. Yeah, that was in 1985.
Okay.
Limitations on pile size, pile length that come into play to be able to use this. Like if you have a 400-foot long stick, it's still working.
To the best of my knowledge, yes. I mean, it still just treats it as a one-dimensional rod. That's probably sizing the pile or sizing the hammer for that much like capacity would be kind of probably the tricky part of that.
I think, definitely getting a 400-foot long pile, you would need a super stiff pile. So, I mean, if you can drive the pile, then you can do the PDA on it, So, I mean, if you get some noodle in there where you're just kind of, doinking the pile, then, but I think if you consistently drive pile with, with a high, stiff pile, it'll work. We've done 300-foot long piles.
Questions. Do you normally do this? Person doing the PDA, is it normally the owner doing that, bringing somebody in, or does that typically work with contractor?
That's a good question.
That's a really good question.
I mean, so like for DOT, we've taken it like where we want the PDA contractor working for us, just because we want them to give us other, brainstorming, helping, but I think it's more consistent or more common for the contractor to, like in the lower 48, the contractor will hire the PDA to work just for them, and you just put in the contract, do PD testing, give us the, thumbs up. But I know our bridge section was, I don't know. They wanted to have the kind of control over making sure that the PDA contractor was working for the bridge section so that we had them in our pocket in case there's any kind of controversy.
All the projects except, well, yeah, see, all the projects I've worked on, contractors hired us to do the work. Or it's been our own, kind of our own project, if you will, so. Just to help verify. When I've been a third party, it's always been the contractor.
All right, thanks for having us.
Yeah, appreciate it. Thank you. I guess, were there any questions online? I forgot that there were some online folks, but.
I like turn them off, but that's all right.
Okay, yeah, folks have kind of already dropped off. Okay. Sure.
We'll see everybody in person today. Hey, thanks for coming.